SwayamPrabha. Digital India. Educated India.
Hello, welcome back to Aerospace Structural Analysis. In the last lecture, which was lecture 4, we studied torsion of circular cross-section shaft in the context of theory of elasticity. So, in this lecture, we will move on to torsion of non-circular shaft. But before we move to torsion of non-circular shaft, let us summarize what we studied for circular cross-section shaft and then translate those concepts to torsion of non-circular shaft. So, in the last lecture, we have done that for a circular cross-section shaft at any arbitrary point P, the torsional the only stress that is acting on the cross section is a shear stress, which let us represent by tau, which was obtained as g into theta into r, where r is the radial distance from the center to the point P. So, from the center O to the point P, we have this distance r, and we know that for a circular cross section the only stress that act is tau, which is perpendicular to the radius and is given by g theta into r. Now, what we have done is that we have resolved the stress into two components in the Cartesian coordinate, two perpendicular component. One was tau x z and other was tau y z. So, now we had also seen that the expression for tau x z was minus g theta into y, and the expression for tau y z was g into theta into x. All other stress component, that is sigma x, sigma y and sigma z was equal to 0, were equal to 0, and the other shear stress component, that is tau x y, was also equal to 0. Now, what we did in the last lecture is that we saw that this stress state satisfied the equation of equilibrium. We have used the equilibrium equation, and we have seen that this state of stress satisfied the equilibrium equation. It also satisfied the boundary conditions also. So, number A, number B is also satisfied on lateral surfaces perfectly. It perfectly satisfied the force free condition in the lateral surfaces of the shaft. It partially satisfied the boundary conditions on the top and bottom surfaces. So, though it did not ideally satisfy the force free condition at the top and bottom surfaces, but it satisfied those conditions to a good approximation, to a practically applicable cross section. Now, from therefore, this state of stress is a true equilibrium solution of a shaft of circular cross section under pure torsion. Now, let us use the condition of let us use the stress strain condition. As discussed in the lecture 3, there would be a stress strain relation which relates the stresses that we have obtained with the strain. So, using stress strain relation, we can obtain that the shear strain tau x gamma x z would be tau x z by the shear modulus G, and that would be minus theta y. Again, gamma x z is del u by del z plus del w by del x. This is coming from the strain displacement relation. So, from the stress strain relation, we have obtained the expression for the strain from the stresses by dividing it with the elastic modulus, the shear modulus, and then by using strain displacement relation, we have written the strain in terms of the displacement u, v and w. Similarly, gamma y z can be written as tau y z by G, which is going to be plus theta x, and that is going to be del v by del z plus del w by del x, again from the strain displacement relation. The other expression that we have is epsilon x, which is the normal strain in x direction, which is equal to 0, which tells that del u by del x is equal to 0. Similarly, so this is a set of equations that we get by using the stress strain relation and by using the strain displacement relation. Now, if we try to solve these equations, let me name it as equation 1, this as equation 2 and this as equation 3 and equation 4. If we want to solve for equation 1, 2, 3 and 4 and try to find out the expression for the 3 displacement u, v and w, you can see that u, if you solve it, I am not solving it because it is slightly lengthy, we can see, but it is very easy to solve. If you solve this, you will see that you will get u as minus theta y z, v as theta x z and w as 0, providing the boundary condition that u, v and w is equal to 0 at x, y, z equals to 0, 0, 0. So, if we use this boundary condition, then from these equations we can get this expression for u, v and w. So, from this expressions as well, you can see that the features for the torsion of circular shaft, that is the cross section is not going to get distorted, there will be no out of plane deformation or warping is satisfied. So, this is what we can write in summary for torsion of circular shaft by solving the equations of equilibrium. So, next we will move from here to torsion of non-circular shaft. So, I have u equals to minus theta yz, v equals to theta xz, w equals to 0 for circular cross section shaft. Now, Sven has observed experimentally that instead of a circular cross section shaft, if we take a non-circular cross section shaft, and then the displacement fields are obtained as minus theta yz, v as theta xz, and w, which is the out of plane deformation or the deformation and displacement in the z direction, that is the lengthwise direction of the shaft, is obtained as theta into psi x minus x comma y, where psi is called the warping function. So, this was observed experimentally, and from the experiment Sven gave this displacement functions for a non-circular cross section shaft. So, if we take any arbitrary non-circular cross section shaft of any arbitrary shape, it could be rectangle, it could be a square, it could be a triangle, or it could be any arbitrary shape. Let this be the coordinate. Then the displacement field is going to be of this form. So, this is called Sven theory of torsion. Okay. So, let us now see what is the difference. The essential difference between cross section of circular shaft and cross section of non-circular shaft is this w. For a circular shaft, w is equal to 0, but for a non-circular shaft, w is equal to theta into psi x y. So, this is the out of plane warping. The other thing that needs to be noticed is that the warping function or the psi is dependent only on the cross sectional axis, that is x and y. It does not vary with the length of the shaft and just depends on the cross sectional axis of the shaft. Now, our next job is to see that the state of stress that we get from this displacement field given by Sven solution, are they going to satisfy the equations of equilibrium and the boundary condition as we have seen for a circular cross section shaft. Now, if these are the displacement function, let us see what are the stresses in non-circular cross section shaft. So, let us see our sigma x, which is E into epsilon x, is going to be 0, because del u by del x is equal to 0. Okay. This is equal to del u by del x, which is equal to E into del u by del x, which is equal to 0. Similarly, sigma y is equal to 0, and so sigma z is also equal to 0. So, sigma y is del v by del y, this is equal to del v by del y into E. Now, v is not a function of y, so this goes to 0. Now, similarly, tau xy, which is g into the shear strain gamma xy, which is g into del u by del y plus del v by del x, that is also equals to 0, because del u by del y is going to be minus theta z and del v by del x is equal to be plus theta z. So, this is going to be minus theta z and this is going to be theta z. So, that is equal to 0. So, the only non-zero stresses that we will be having is tau xz. Tau xz is going to be g into gamma xz. Now, what is gamma xz? That is going to be g del u by del z plus del w by del x. Now, if I substitute this displacement functions here, displacement fields here, I get this as g into theta into del psi by del x and minus y. This is the expression for tau xz that we get by from the displacement field. Similarly, tau yz, the other remaining shear stress, is g into gamma yz, and that if you write it as g into del v by del z, you will get this as g theta. This is what we get. Now, therefore, let us see, similar to what we did in the last lecture, let us see whether this state of stress satisfies the equilibrium condition. So, let me see. So, let me write down the equations of equilibrium and let us see whether this state of stress satisfies the equilibrium condition. So, the first equilibrium equation is let us consider that there is no externally applied body force. So, this has to be equal to 0. Now, out of this I know that sigma x equals to 0. So, I have seen from here that sigma x is equal to 0. Tau xy is equal to 0. That also I have seen from here that it is equal to 0. Now, tau xz is not a function of z. So, as you can see, this is not a function of z and this is just y. So, this whole thing is equal to 0. So, the first equation of equilibrium has been satisfied. Now, let us see whether the second set of equilibrium equation is being satisfied. Whether this is equal to 0. Now, let us see, tau xy is anyhow equal to 0, sigma y is equal to 0. Now, again tau yz, as you can see from here, is not a function of z. So, therefore, this whole derivative goes to 0 and the second equation is satisfied. Now, let us move on to the last equation. Okay, so now out of this we can see that sigma z is equal to 0. So, this part is gone. Now, what is tau xz? Tau xz is this, and this can be a function of x. So, let me write down what is del tau xz by del x. So, that is going to be g theta. So, from this we are getting g theta del 2 psi by del x square, and then that is all we are getting, and from this we are getting g theta del 2 psi by del y square, and that should be equal to 0. Now, the third equation of equilibrium, please note that it is not getting satisfied unless the warping function psi is such that it satisfies this condition. So, unless I have a warping function psi that is satisfies this condition, so what we see that though this displacement field proposed by Sven satisfies the first two equilibrium condition, but the third equilibrium condition will not be simply satisfied unless we choose a warping function psi in such a way that this condition is being satisfied. Therefore, I get one criteria on the warping function. So, this is my criteria 1 for the warping function. Now, let us see whether the boundary conditions are being satisfied. So, let us move into the boundary conditions. So, similar to the torsion of circular shaft, the boundary conditions on the lateral surface So, similar to torsion of circular shaft, let us first check whether the boundary conditions on the lateral surfaces are being satisfied. So, as we know, for the cylindrical shaft, the lateral surfaces are free from any force. So, it is a force free surface. Therefore, x hat, y hat, which are the lateral forces per unit area, should be equal to 0 for the lateral surfaces of the shaft. Now, x hat is going to be sigma xl Now, we have let us draw an arbitrary non-circular cross section shaft. So, on the lateral surfaces, say at any arbitrary point, say this be the normal. This is the x axis and this is the y axis, and this is the normal at any arbitrary point P on the lateral surface of the shaft. Therefore, L, which is cos of n with x, let this be alpha, can actually be written as this is dx, this is dy, this is ds, and this is dn. So, this is basically cos alpha and cos alpha can actually be written as minus with dy by ds. From geometry you can see that L can actually be written as dy by ds. Similarly, m, which is cos ny, can be written as sin alpha, which is going to be minus dx by ds, because x is in the opposite of the positive x axis, dx is in the opposite direction of the positive x axis. Now, let us see. So, sigma x is anyhow equal to 0, tau xy is equal to 0 and n is equal to 0 for the lateral surface. N is in the direction of the z axis. So, it is always normal to n, the normal to the lateral surface. So, this is anyhow equal to 0. So, this is 0. So, this equation is satisfied. Now, let us move on to the next boundary condition, which is tau xy Now, let us see. Tau xy is anyhow equal to 0, sigma y is equal to 0 and n is equal to 0. So, this equation has been satisfied. Now, let us move on to the third equation, where z hat is equal to Now, out of this, sigma z is equal to 0, tau x z is not equal to 0 and tau y z is not equal to 0. So, let me write down the expression for tau x z. Tau x z is g theta Now, in place of L and M, I can write this as so, but z is equal to 0 on the lateral surface. So, what we get in turn is that therefore, in order to satisfy the boundary condition on the lateral surfaces, we have to choose a psi that is going to satisfy this condition. Now, therefore, we have two criteria imposed on the warping function psi. So, we have the warping function for non-circular cross section psi has to satisfy equation 1 and equation 2 in order to satisfy the equilibrium condition and in order to satisfy the force free condition, boundary condition on the lateral surfaces of the shaft. So, in order to obtain the solution of torsion of a non-circular shaft using Saint-Venant's displacement fields, we need to find or get hold of a warping function psi which will satisfy these two criteria. Only then we will be able to find out the solution for the torsion of non-circular shaft. This is about the boundary conditions on the lateral surface. What about the boundary conditions on the top and bottom surfaces? If we look into the boundary condition on the top and bottom surfaces, you will see that they are similar to that of the circular cross section shaft, where we will see that x hat needs to be similar to tau x z and y hat needs to be similar to tau y z. Okay, exactly. So, this is exactly similar to circular cross section shaft. So, I am not re-deriving it. You can derive it on your own and see that this is the criteria that the shear stresses need to satisfy on the top and bottom surface, which can be taken care by using the approximation that we have discussed in lecture 4. Thank you.